Okay, so good morning again, everyone. And my name is Maria Luisa Quarta. I'm here with my colleagues Marco Follegani and Andrea Ricciardelli from the Mio company that are the leader of the use case about food security that will be presented today. And together with me, there's also partners from the EO4EU project, Kakia Panagidi and Stas Pablo, that will support us during this workshop session. So I will share my screen and start with the presentation. Sorry, just let me get the, yes. Okay, so as said before, this use case has been implemented in the context of the EO4EU project. And the objective today is to tell you how the Earth observation data can support the food security domain. Well, a few words about the project. It is an innovative project funded by the European Commission in the program Horizon Europe with the objective of developing the EO4EU platform to facilitate basically access and use of Earth observation data for environmental, governmental, industrial, and operational forecasting. Of course, the target is covering several domains, several sectors, and as it is quite transversal, and the objective is to facilitate the retrieval, the processing, and the integration of new data sets, but also to support these domains through the use of innovative technologies such as machine learning algorithms and advanced semantic annotation. The project is approaching its end, and 7 different use cases have been implemented that are covering different domains, different sectors. So from the healthcare, the ocean monitoring, the forest ecosystem, the soil erosion, the environmental pests, the civil protection, and of course the food security. There have been several workshops describing them all. So in case you're interested, that there's still some coming in the next days. Regarding the food security use case, this focuses on assessing the impact of climate change on the productivity of essential crops, such as the industrial tomatoes. So more specifically, the aim is to promote sustainable agricultural practices and to support farmers, producers, and other types of stakeholders in making informed decisions to strengthen resilience to climate-related challenges. Indeed, it is well known that global warming has a major and negative impact on field crops. But not only high temperatures are affecting the crops, while throughout the production season, crops are very sensitive to different climate events, extreme events, sudden and unexpected weather variability, and also local water variability are among the most impacting factors. So as a consequence, crops are increasingly subject to stress phenomena that lead to delays in the phenological phases of plants and results, of course, in a reduced production. As a consequence, it is necessary to find new tools to guide farmers towards more sustainable choices. And in this context, the Earth observation data play a crucial role as an innovative tool to address the challenges of the agricultural sector. Satellite imagery, indeed, and also data derived from remote sensors enable large-scale monitoring of crop health, but also of water resources, as well as pest and disease dispersion, and of course, climatic condition trends. And this capacity for continuous and detailed monitoring enable farmers to take timely actions and adopt more effective and sustainable management strategies. So the main objectives of this use case are then connected to these capabilities of the Earth observation data, as thanks to these data, it is possible to analyze the climate change impact on crops, estimate the risk of crop losses in the future, identify new favorable areas that are considered better for specific target crops, but also identify crops suitable for new conditions. So it is clear how Earth observation data have applications in a variety of agriculture-related sectors. We go from agricultural insurance, which can better assess and manage climate-related risks and crop losses, to precision farming, which uses this information to optimize inputs such as fertilizers and irrigation, but also to financial markets, which benefit from more accurate forecasts for investments and trading decisions. So in the context of the EO4EU project, the food security use case can benefit from the EO4EU platform implemented in the project for different reasons. First of all, the platform allows for an easy access to some data sources that are needed to run the implemented model. And in this case, the so-called knowledge graph component is very useful for the use case. We will come back to this component in a few minutes. But basically it allows to define, to search for data and services based on selected keywords. Through the platform, it's also possible to download data to build the workflow that it's needed to run the whole use case, to visualize the obtained results, but also allow the users to customize the model. By changing, for example, the area of interest or the time range for the specific analysis. In the schema, it is summarized the whole workflow of the use case, of the food security use case, that starts from the data collection, that of course implies also preparation of data, particularly production and climate data, and goes through the data analysis and interpretation, where we have implemented several climate indicators that have been correlated to the crop yield in the end. And then we made use of machine learning models that have been trained with selected input data to provide an inference that by integrating climate scenario allows us to predict the yield crop in future scenarios, and so to identify favorable areas for the specific crop. This workflow is easily mapped towards the different components that are part of the EO4EU platform. So on the left side of this slide, you can see a screenshot from the platform where you can distinguish between the different components, starting from the data source component that, as I said before, allows to access the input data needed for running our model, and also includes the crop fusion component that allows for the pre-processing on data and features extraction. And then the core of the workflow, it's represented by the crop prediction that includes the machine learning model inference, which allows to produce the data output that are represented by basically an estimation of the yield classes for the target crop. And of course, the whole process will be explained more in details in the next minutes. So basically, a new yield classification approach has been implemented, and you will see how we divided the observed crop yields into classes, quartile-based classes, thus enabling a structured assessment of the productivity levels. So I will now leave the floor to my colleague Katia, that will give you more detail about EO4EU platform. Katia, I will stop sharing my screen so that you can...
Thank you.
Thank you, Katia.
Just a second to make the note. Okay, share. No. Do you see my screen?
Yes, thank you, Katia.
Okay, perfect. So thank you, Maria Luisa. It was quite thank you for your presentation. What we would like to present today also through this the presentation of this use case is EO4EU platform is a project funded from the European Union, as also presented. And what was the main goal of this platform was that I would like to keep in your mind, that we would like to facilitate the users to download, process, and visualize the data coming especially from Earth observation data. So what we would like to do is to create a whole new Earth observation data ecosystem to provide tools through machine learning, fusion, processing, algorithms that can be provided to the user, to present it through a common schema, because we already know that for the data coming, especially from Earth observation, that we are having data here and there. And of course, to provide also tools like augmented reality and data visualization for the results of what they would like to see, either from the raw data or from the processed one. Of course, we provide also them the infrastructure in order to run their own processing or their own use case. What were the main challenges? The main challenges, of course, were that we are having diverse sources of information. Sentinel 1, 2, and 3 are provided through different API providers in different spaces with different formats. It was quite, if you can say, quite a challenge to make a common schema in order to harmonize all of them. Of course, data were here and there with quite different APIs, so we have to get in this, if we can say, common interface that the user goes through the platform and he can search all the data sources in once. Of course, the difficulty, as I said, to find and retrieve the relevant data. And of course, the tools that we have in order to process them. Use case owners, as here we're discussing today, we are having a lot of discussions during the project in order to understand what are the main challenges, what they don't find to other APIs, what they don't find to other platforms in order to fill the gaps. As you can see here, this is the architecture. I don't want to go in deep details. What I would like to keep in mind is that EO4EU ecosystem is a one-stop shop for the processing and the downloading of Earth observation and in general geospatial data. So we are having a tier of data, as you can see in the left part, and what we are calling knowledge graph that harmonizes everything. We are having a layer also of machine learning and fusion that process the data in predefined ways and provide it to the users. We are having the visualization, of course, at the end of the data. Either we are talking about just CSVs as numbers provided and visualized in graphs, or as geospatial images presented on top of a map, or either as a PDF or as a file explorer. Of course, we can use augmented reality and virtual reality if there is a case. And all the other is the backend, is the hard workers, because every time that a user is going to run a workflow, imagine that we are talking about quite a big data needs. A dynamic cluster, a dynamic ecosystem is provided especially to the user, is created in order to support this processing and ends at the end of this workflow. So why a user to use EO4EU? Why to come here and use this platform? As I said, is one-stop shop. You don't need to worry about different username and passwords, different needs of APIs. You select the data source that is already integrated in our case. You can run and just with an easy way, if I can say, to create, if you can say, workflows, and then you can get the data quite as this easy. Another thing is the infrastructure. You don't want to worry about infrastructure or that your ML algorithm is going to need 2, 3, 4 days in order to run for a specific area. These all are provided by EO4EU. Machine learning and fusion models that we have created with use case owners in order to support these complicated tasks. And if you are having, for example, you are an expert in the data processing and you would like to run your own notebook, then it's also a case in our platform. And of course, AI, augmented reality, virtual reality technology. So, for example, a user wants to run an application to EO4EU. What we would like to do, first to register in the platform. You are entered through your username and password. You are searching your specifically data sources, like, for example, in our case, CMCC, the climate data sources. You can select them, create a workflow, start your workflow, and then visualize the output. I am an expert, so I would like also not only to download data that I can see that it's okay, but I want also to process it with uploading my own data in order to integrate it in one, if you can say, chain of actions. When I'm talking about workflow, what we are meaning in our, if you can say, in EO4 is translated in EO4EU, is a chain of action. What is a chain of action? To download data, for example, to merge the TIFFs in quite a common file, to go through an ML algorithm, and then to output the result. A user also can make it, if he's, as I said, an expert, to upload notebook as his own notebook here. So he has his own data coming from EO4EU. Everything are integrated in one processing from his own, because he would like to test his own ML, his own processing algorithm, and then he visualizes the result. And he can also save this as a workflow in order to do it again and again. Another thing that was requested, not in this case, but we are going also to present it, is to run it through an API. We are compatible with OpenAPI, that is quite a common protocol for data providers. And what you would like to do is to run your own code daily, or you can run your own goal weekly, to test things. For example, for the fire risk assessment of Italy or in Greece, is something that you would like to make a prediction daily. So you create a chain of code that you can run it again and again, and then EO4EU is just, if you can say, a black box that serves you with either data or the output of this data. Here, if you can say, you can just push the red button. So what you're going to see is a dashboard. The dashboard has some specific, if you can say, chain of actions. You can select the data sets in order to search data through the knowledge graph. You can create a workflow, so you can select different data sources in one, if you can say, workflow, as again is a quite, if you can say, example. The workflow editor to define the different steps that you would like EO4EU do for you for the specific data. And then the output is going to be disseminated to you either as data visualization or map visualization. Of course, you're having, as in the left part, the notification section in order to be notified in each step that we are going further. There was a question from a user why we are providing as a steps and not as a time estimation. And the answer is that we cannot make predictions. For example, you can download a huge volume of data of the whole world, so the download of data can last for 2 or 3 hours. or you can select smaller area, and this can be downloaded in minutes. So we are providing an estimation of all the steps that you are doing in order to get the data that you want. Knowledge Graph, as I said, is the main tool in order to harmonize all the data sources. You can select, as Maria Luisa said, specific area of interest and specific date time, and it's provided also some information about the description of the dataset. Here is how we build some workflows. And what I would like to see is that we are having the chain of actions, what you can do, or you can upload your own code by your own. We support Jupyter Notebooks. Here is, for example, a chain of actions. Data visualization. Data visualization is the dedicated part. For example, if your output is a CSV, is something like a text, is something that can be visualized through a graph, through bars, or through, if you can say, mathematical figure. We are having the data visualization, and we are having also the file explorer. In the right part, you can see the output, for example, of a PDF that is for this specific use case, the mice and the tomato yield forecast for a specific area of interest. Maria-Louise is going to be explained quite in a while. And of course, we are having also augmented reality. Augmented reality is that we are creating digital elevation model for a specific area of interest that is provided while you're searching your data. And this data, these tips are going to be resampled on top of an area. And why this, for example, is quite important, because as a user, you would like, through the virtual reality Oculus metadata, to provide to your, if you can say, colleagues. Here we can see that we can select, for example, the workflow that you have, and you can see the output of a specific area in a 3D map. You can take it, you can select it in the space. For example, I think at the end of the project, we are having the fire forecasting. So you can check in quite close to your data, or for the presentation needs, the output of these digital elevation models provided by EO4EU. Another, if you can say, also interesting part is the augmented reality. That if you're having the processing, for example, of area, and you would like to be presented in the camera of your own mobile phone, it is also possible. In our specific paradigm, for example, it's only a blue line, because we are talking about this data are in a scale of a city, so we are quite small part in this specific, if you can say, scaling. But okay, if we are having a more, if you can say, detailed map, you are going to see the output like a forecasting of soil in your mobile application. And this is an overview of EO4EU. I don't know if you have any questions.
Anyway, we are going to have a question and answer session later on, so we can, like, the tenant can think about them, and we can collect them at the very end. Thank you, Katia. Thanks a lot for this presentation. I'm going to share my screen again, as I would like now to provide you with more details about the methodology that we applied to implement our use case. So, but before going into details about the methodology, I just wanted to share with you a few considerations about the challenges that we encountered, of course, during the use case implementation, as of course even the most innovative tools have their limits, and just as all implementations, so there are difficulties. So first of all, we want to clarify that our expertise, is mostly on the algorithm implementation and climate indicator generation. In this specific use case, of course, we are expert in Earth observation data exploitation, but just to clarify that we are not expert of this specific crop, and we had to interact a lot with several stakeholders that supported us in the definition of the requirements for the methodology, so that the initial objectives were recalibrated based on the difficulties that we encountered during the development of the use case. And of course, there are limits that are connected to the unavailability of certain data, like abiotic factors other than temperature that can influence the crop yield. We have very few information on climatic stresses, such as the critical duration of extreme weather conditions and how the crop can recover after a severe stress or an event. There are still some unresolved issues, and we hope that at the end of this session we can have a discussion about this. If any of you as expertise in the domain maybe can provide us with some insights. And of course, we are open to any potential alternative solutions to reach the objective that we are that we have in mind. Of course, the use case also is very much dependent on the project progress and adjustments. So we had to stick with technical implementations timing. And we, of course, are aware of the fact that the technologies that we are using for this use case are evolving continuously. So for sure, after a 4 years project, there's room for improvement. That said, let's go a bit more in detail in the methodology for this use case. So first of all, the industrial tomato was selected as the first target crop because of its key role in the Italian agri-food sector. And then this was joined by the maize crop, and this was done to demonstrate the applicability of the implemented methodology to different crops, so its scalability. Of course, the study areas were chosen to represent a diverse range of climatic conditions. So we first of all collected data on the Italian territory, but then we realized that in order to make the whole methodology more robust, we had to extend the data set also to another country like Spain, that it's another important tomato producing country. So we integrated those data as well. And for what regards the maize crop, the area of interest covered the Italian territory, but also the French territory, because they have similar production for this crop. The relevant data for this case study include, of course, Earth observation data, simulations, projections, and statistics, which have been carefully selected. These include Copernicus ERA5 data with the temperature and precipitation. For those that are not familiar with this data, the ERA5 data are generated from a combination of Earth observation data and numerical weather prediction models through a process that is called reanalysis. And the purpose of this data is to provide an accurate and long-term view of climate conditions, supporting, of course, climate change research like this one. Then you make use of other Earth observation data like Sentinel-2 that allow the building of vegetation indexes. We used very high resolution data sets from CMCC simulations, both historical and projections, so climate scenarios that are developed by the Center for Euro-Mediterranean Climate Change. And we made use, for what regards the crop yields and their distribution in Italy, of the statistical data source, the so-called ISTAT. Then the digital elevation model was used to discriminate highlands from flatlands, where most crops are expected to be present. Then we integrated also soil information from the soil grid data source. So parameters like clay, sand, nitrogen, dissolved organic carbon, pH of water. And this is a global digital soil mapping system that provides soil properties at the global scale. And finally, of course, we made use of the European territorial boundaries. As said before, we started from preliminary studies that involved many stakeholders because we really needed to shape our methodology, trying to understand what were the most important factors that to take into account when studying the crop resilient towards climate change. So we, thanks to the support of the stakeholders, we could identify the trend of cost, the area and production for the specific industrial tomato crop, the optimum of the temperatures, what are the main stresses, the killing temperatures, what are the water resources requirements, some thresholds for these values, and of course, what is the growing season, what are the target months to be analyzed, and also eventually evapotranspiration needs. So after identifying all these like basic information, we started extracting the data needed to integrate in the process for the agricultural yield analysis. And three main information sources were used. Economic production data that include cultivated area, total production and yield per hectare, daily climatic data, so with all the different statistics like minimum, maximum, average temperatures and rainfall, but also hourly climate data, because being more detailed, they allowed us to capture extreme events, rapid changes. And these were then aggregated into a single data set where each year was associated with derived indicators. This allowed us for a robust comparative analysis and for predictive modeling, helping to assess the impact of climate on productivity. At the end, we were able to build 84 different indicators that we broke down by crop cycle period. So we took into account the entire growth cycle from April to September, the planting and initial growth phase from April to June, the production season from July to September, and a critical month that is May. These indicators were based on parameters such as precipitation, temperature, the combination of the two, soil texture, soil content, so nitrogen, organic carbon intensity, pH levels, and in the very like last phases, we also included the radiation and moisture. So after building these indicators, of course, we wanted to correlate them to the crop yield. And I will show you now a few results through these paired plots that have been that need to be interpreted using the a correlation index. So on the right side, you can see what is the scale for the correlation index, which tells us basically how much this parameter, in this case, it's the temperature, all the different indicators that we built for the different periods are correlated to the crop yield. You will see that apart from telling us whether this correlation is positive or negative, actually for all the indicators that we examined, the correlation is quite weak. And so even if you see sometimes that like the color is quite dark, that means that's high correlation, it is not high enough to tell us that it's a strong correlation between certain parameters, certain indicators, sorry, and the crop yield. And this is the same also for the correlation between crop yield and precipitation indicators. We can see in this slide like just a summary of both precipitation and temperature, where we take a few indicators that look more like meaningful. Again, there's not a clear and a strong correlation. So what we answer ourselves to give us like an answer about this, so what we realized that actually comparing the correlations with the various indicators with yield can be seen through linear relationships. So what does it mean? That looking at the specific correlation, it means looking at, as said before, at linear relationship between two parameters. But we realized that our machine learning model that we will see in a few minutes, in the end, has a quite high score of efficacy. For those that are not familiar with machine learning models, there is a way to evaluate the efficacy of the model and through a score. And our model reached almost a 0.74 score. That means that 70 times out of 100 the model is correct, which is quite a good result. What does it mean? That the model basically, by combining all variables together, it's capturing all these non-linear relationships and complex interactions that are not possible to see with these linear correlations. So it's like the model is finding hidden patterns for us. And this is very interesting because it means that if we at a certain point succeed in integrating our methodology with further information, such as information about irrigation of the crops, or information about fertilizer. So all these factors that we know are impacting the crop yield, but that unfortunately we couldn't include in our methodology, then of course the model will be even more accurate. And so,
Maria,
yes.
if Luisa, if I can
Yes, please.
comment about that. Basically, this is what we were expecting in the beginning when we started designing the use case. We were basically aware that the single correlation, the single parameter, wouldn't be able to describe the effect and the phenomenon concerning the impact of climate variables to the crop yield. The combination, we were basically aware that a combination of different parameters would better describe the impact of climate trends, even though at the beginning of the use case, we really didn't know exactly what was the right combination, which is something that we discovered during the test, the implementation of the algorithm, and what we also discovered by means of the implementation of machine learning, that, as you just said, is able to catch the hidden combined impact of different parameters to the target variable we want to investigate. So this is I don't want to say what we were expecting, but it is some way the results that are in line with the scope of machine learning application and machine learning techniques in this kind of analysis. Thank you.
Thank you, Marco. Thanks. So this is just to show you how also the correlation between crop yield and soil indicators has a similar pattern. So there are a few correlations, particularly for the nitrogen, for example, nitrogen content, but nothing really explicit, let's say. And here we just summarize, let's say, the top 20 correlations. So what are the indicators that showed the highest correlation, both negative and positive correlation with the yield, and the related values. So to actually better assess the influence of climatic conditions on the physiology of the tomato plant, we also analyzed the normalized difference vegetation index. So again, the Earth observation data comes in support of our purposes, as we made use of Sentinel-2 data for this analysis. And this part of the study basically was to gather information on production and impacts in the absence of precise territorial data. So basically, each image was cropped according to the selected fields, and the mean and median NDVI values were calculated for each field in order to find trend curves that can be generated for each field. And since crops share the same growing season but vary in start and dates, then provincial NDVI curves were constructed by basically normalizing the data to relate them to the respective production yields. In addition, we built a sort of reference NDVI curve in order to facilitate the comparison between the different NDVI curves and identify the the possible anomalies. And again, as I said before, this shows how Earth observation data can fill certain data gaps, especially in studies like this, where our target is at a large scale and is not limited to a single parcel. So going finally to the core of the methodology, which is based on the use of a machine learning model, all the collected information were used to train an algorithm, a machine learning model for crop yield prediction. For those that are unfamiliar with this type of technology, basically these models work by training through algorithms that allow the model to basically learn how to map input data to the desired outputs. And it's a way to optimize the internal parameters to minimize the errors. Once that the model, is trained, then is evaluated, as I said before, to verify its performance and its accuracy. If it meets the required standards, then it can be used to make predictions, like in this case, for yield trends of the selected crops. The data that we use as an input for the machine learning model include the statistical data for yield crop, the Copernicus ERA 5, the digital elevation model, the European territorial boundaries, and the soil data. After having trained the model, then the model inference phase comes that processes the input data to produce the expected output. The type of model that we selected is an artificial neural network for classification, which basically is based on a supervised learning. That means that it learns from examples with known answers. It's non-linear, as said before, and for this reason can capture complex relationships in data. It's highly configurable, so we could select specific parameters, and it's quite versatile. So the reason for choosing this model is, as said before, because of its non-linear relationships, and we know that the agricultural factors involve complex and non-linear interactions. And also, it allows us to take into account multiple simultaneous factors, which are better handled by classification models. For the inference part, the input data are represented by the CMCC climate projections, so the climate scenarios. Again, the digital elevation model, the European boundaries, and the soil data. So the result of the model brings us to something like this. Basically, we estimated, the model estimates the crop yield in 4 different classes, in specific climate scenarios. So this example regards some provinces in the north of Italy for the year 2041, where you can see through different colors the expected crop yield. And it was very interesting to run the model for different years and in different areas, as you can see the potential, because regions like, for example, the Emilia-Romagna region or the Veneto region that were expected to be less resilient in the future towards the climate change, in the end, actually, it seems that they will have quite important crop yield amounts because of their resilience. Probably the situation, of course, is quite different from the region in the south of Italy, where we have seen that in future scenarios, the areas will be more impacted. And this will allow the farmers, of course, to, from one side, to plan how to differently cultivate their crops, either changing the type of crop if they want to use the same area where they are working on, or just changing area if possible, of course, where basically the crop looks in more favorable conditions. As said before, following the successful implementation for tomato, the methodology was also applied to the maize crop, which is one of the most widespread crops in Italy and Europe. And that was selected not only for its relevance in food systems, but also because its growing season is similar to that of tomato. And of course, this makes easier to use, to reuse the same methodology. Indeed, the same machine learning model architecture is used for the two crops, but the model in this case is retrained from scratch using, of course, maize-specific data. And in particular, the model was trained on maize yield data, climate indicators, and territorial variables that are tailored to the maize crop cycle. And as I said at the beginning, the data are retrieved from the area of Italy and France. This, of course, confirms the scalability of the use case-free workflow to other crops, and the user can make use of the methodology to customize the model just by simply adjusting the calculation periods of climate indicators based on the crop calendar, on the reference crop calendar. And the entire workflow can be transferred to other strategic crops, thus contributing to food security planning in the context of climate uncertainty. Okay, now that we had this overview on the methodology, I will pass the floor again to our colleague Katia to show you a bit more in a practical way how the use case can be run through the EO4EU platform. So I stop sharing my screen and I leave the floor again to Katia. Thank you.
Just a moment. Okay. Wait. Do you see my screen?
Yes, thank you, Katia.
Okay. So what first of all you can see as a user of EO4EU, our first page, if you can say, after the registration, how you can register, for example. Let me check here. Just you go to the page that I'm going to send you in a link in the chat and create an account. In the create section, what we need for you is a first name and last name, email, username, password, and a confirmation of password. Of course, you are registered. If I'm not mistaken, you're going to receive also verification email, and then you are going back to the portal of EO4EU. What you can see here and how you're going, what are, if you can say, the key sections for you. First of all, in the left part, you can see the user guide. In this user guide, probably I'm saying just a general information that all the use cases and all the components, we are providing a tutorial for you. Of course, this tutorial is enhanced, and we are trying a little bit to provide the new, if you can say, descriptions of the use cases. Here we are having also the use cases, and use case 3, it is the previous version, I believe, till next week we have uploaded all the new, if you can say, uploads with the new algorithms that we are going to present today. So you're having two options. First of all, as a home to search for data. The data that we need for this use case is the following. If you're just select from the sources CMCC data source, and we are typing like climate, you are going to see two, if you can say, data sources integrated for this specific use case. And here you can check if you're going, you can select an area, if I'm not mistaken, for example, the area of Italy. Just let me, okay.
Yes, just sorry to complement Katja. It's important here to select a small area, let's say at the provincial scale, but this depends not on the model, but on the climate data source, because the CMCC data have, let's say, a threshold of data retrieval. So it's important to work on a small scale.
Probably we are going to provide also with the specific polygon that you are creating in the tutorial, and of course, if it's possible to have an area in land and not on close to a sea. If I can say as a comment for this specific use case that we are talking about soil. Okay. You can select some date range. I think it's not here is relevant, the date range, if I'm not mistaken. So we are having several options. What options is coming? I'm sorry, but I'm going to have a cheat because we're having a lot of data sets. Total precipitation and 2 meters. Here you can select the variables.
Yes, it's 2 meter temperature. Exactly. Thanks.
Exactly. And total precipitation. What is the format of the output? Is an HCDF. What is the temporal coverage? We are talking about 2025, if I'm not mistaken.
Yeah, the user can select the preferred year. Yes.
We can select, for example, 3 months in a row: April, May, June. This is what we would like also to enhance, that you can select all the days in a coverage. However, this is also coming in contrast with other user requirements that they would like to select specific dates of a month. But we are going to figure out how we can select. For example, here is what we are going to select: all the days of a month. Okay. All the hours, if I'm not mistaken, is all the hours is 24, correct, Maria Luisa?
Yes, exactly. Yes, it doesn't look very handy right now, but our technical
I'm going also to show you also.
Yes.
Yeah, I'm going to show you also from the notebook that is more, if you can say. And there is no vertical. So we're generating a script, and this script, as you can see, it creates a script that we can save it for the rest, how to say, for in order to be selected in our workflow. As a user, I can set and I can save all my preferences, as if you can say you are going in an e-shop and you are selecting all the products that you would like afterwards to process and to download. That's why we're talking about Workflow Creator. Another thing that probably you are going to need is NUTS. NUTS, it is data coming from Eurostat. There is no way we are going to save it afterwards. What was the difficulty in our use case? While we are in the starting days of the project that we have selected a bunch of data sources. First of all, these data sources were changing the API, so it was quite difficult, as we said in my presentation, to harmonize all the data sources. But we had also data sources that they were needed, and we haven't beforehand, if you can say, defined it as a data source. And also, while the project is going to finish, probably we need to enhance our platform with new datasets. So what we would like to do, it was to have a user that he can upload his own, if you can say, data sources that he believes that are useful for the future of this project, and this data can be publicly available to all the users. That's what are, if you can say, the nuts section and what we are having as a nut. So what if we are selecting, for example, these data sources, what we would like that we can create is to create, for example, soil test, and select the data sources that you would like to integrate together and create a workflow. I'm doing a little bit, I don't want to waste your time. Another thing, and this is in what we have created. What we are meaning is the following. In the workflow editor, you are going to have a draft in which we know beforehand that this workflow has the data that you have selected, and we are downloaded automatically by our part, by the platform part, okay? With all the variables. This is similarly can be done also through a notebook. If you are an expert user and you can install EO4EU utilities, we are going to provide you this notebook. You have to download, the libraries. We are having also EO4EU API utils that you can select it through a pip install that is quite easily. Just give it some time. Okay, I'm importing some libraries. I'm defining my username and the password that I'm using. It is the same as I entered in the platform. I am connecting to the platform. I can list all my use cases that I'm having up and running. You can see it's the same image that I'm having in the portal. A status of workflow is the following. It's published. That means that you have published, processed, probably finalized. Stopped, that I have stopped this workflow because I don't want to be active anymore. And compiling, that he needs some time in order to compile until to reach the published status. Here I can set similarly the climate CMCC and of course the in situ for nuts. Okay, I can also get some requirements about these two, about the datasets that I have searched. Here are some details. I can get the script for this one. I can get the same script as for CMCC and this ADS process. What I would like just to know is some of the users are more familiar with this type of description because it is the usual part in order to download data from these services. That's why I believe it's more, if you can say, if you're familiar with the downloading of this data, you're more familiar with it. Either the way, you can do it either from the graphical user interface, either from the code. We're having also the meta info, and we are creating a new workflow as use case 3 with these two datasets again inside of this workflow. So whatever I can do with the graphical user interface, I can do it also through a notebook and the code that we are going to provide it to you. All these things is to get data that I'm going to download in my own, if you can say, infrastructure. What I would want to do next is to, as I said again and again, to create the chain of actions. The most, if you can say, easy chain of action is the following. That I'm having a data source and a data output. What I meaning? To get the data, download data, and have it in a specific space. That is the simplest way, chain of actions. Another thing, that in our case, in use case 3, we're doing the following. We are having data input and data output. Of course, probably I want to demonstrate it through the graphs, or if there is a need, so I'm going to connect it with customer face. That is what we are saying about the visualization. And I'm going to use one fusion algorithm that is a use case 3. Not saying, okay, crop fusion. If you want to see what this algorithm makes, you can see that get some CSVs and what he's done it through to create some indicators to create the output of a CSV. Just to comment that use case 3 started as quite with his own data source. They changed a lot the neural networks. They were quite into this project. So I would like to thank them. And Maria Luisa and all the team of MEO, because they have made a lot of changes and they evolve a lot the algorithm. And of course, we're having the model of machine learning is use case 3, where is it? Crop prediction, that we're going to predict the crop. Okay. All right. The algorithm needs also some in situ data. In situ data are data that you can upload it from your own. It's your own data, and you upload it from your own, if you can say, environment, like digital elevation model that they would like to create for this specific area. So in this case, I'm having a zip that it's also is going to be provided to you that contains only these digital elevation models. And with this chain of actions, we can save and publish. When I'm saying publish, I'm meaning starting my workflow. This means that afterwards, we're going to create dynamically the cluster. We are going to automatically create all the resources and starting step by step to have the status of this, if you can say, algorithm and chain of actions. You can see here that we are having the publishing, and probably you can see also some green dots. These green dots means the following, that the components are active, they have started, and while we are going to have some, for example, if you're having, this algorithm is going to last for, I think, 1 hour in order to finalize and make the predictions. So in order to download and not go again and again, where are we? We are going, for example, here, data source finished successfully. So we have go through the downloading of data. Now we are in the cropping, and after the cropping is finalized, we are going to the crop prediction and then to the output. So you know in each step, what is the status of the components. So here we are seeing that the fusion pipeline has started. We are meaning everything sequentially. So a component is going to be notified after another component has been ended. I don't want to waste your time. So like cooking recipes, I'm having here, okay, and already, if you can say, algorithm that was run. exactly with the same process. And what you are seeing here in the file explorer is the following: the output of all the components. Here you can see the source. We are having 3 data sources. This is the NAT that we have requested, the in situ, and the climate projection, the net CDF that was downloaded. We are having the output of the fusion that is a CSV. I can check in each step all the files that I can download it locally in my personal computer. And of course, the result of the crop prediction that you can see that is a CSV, and also some PDFs about that helps the visualization of the class identification. I'm sorry, let me share the PDF.
Yes, just to complement while you look for the PDF, Katja. Basically, the results can be seen in 2 different ways. As a table, that's why also the CSV is available, that are basically numbers of the classes corresponding to the crop yield, or as a map with the legend with the different colors, showing in which class each of the area of interest falls for the crop yield.
For example, for the CSV, if I'm not mistaken, is this table that is created for fusion for the specific area. It has a lot of variables. Probably I'm not an expert, but it means something for you.
Yeah, these are basically the indicators that were included in the analysis in the model. So one can also compare probably the values of the each indicator corresponding to the crop yield.
Oh, no, crop fusion. And the result is output. Okay, so we're having this.
Yes, exactly. These are basically the number of the class for each of the 2. In this case, we selected a very small area, 2 provinces, Cremona and Lodi. And they're for the specific year, the 2025, the class, the crop yield class is the number 2. And if you look at the legend, you will know exactly what is the quantity with respect to the hectares. So this is how to interpret the results. And the same can, and in this case, you can see that together you have the yield prediction for tomato and for maize. So while in the case of the maize, that the class was 0, in the case of the tomato, the class was 2. So one can also, analyze them together. Thank you.
So, you're welcome. So this was, if you can say, our main. I know that's quite a lot of information. You can see here the notification. It's a quite new platform that needs time in order to be familiarized with that. And we did a lot of things that we are having, for example, a comment from some users in order to upload in a common space all the algorithms and what they are doing, all the updates. But we are here. We are here in order to resolve any questions, to help you. I'm stopping the sharing just to share in the chat the link of the dashboard and also the email of the technical team, that you can also ask for any questions that you have while you are interacting with the EO4EU platform. And of course, we're more than welcome if you want to have some hands-on, to ask you questions, to make a registration together.
Yes, I can maybe share my screen again. I have just the last slide to trigger discussion here.
Yes, of course.
I can, just give me 1 second. Yeah, so this is basically based on a slide that I showed before. We, as anticipated, there are some limitation in the methodology in the system, but of course, this type of occasion like the workshop, it's useful for us to both collect feedback, comments, and try to improve both the methodology and the technology that we are using. So if you are aware about any type of data that maybe we can use to improve the model, or any type of requirements that we are missing here, for example, or all these unresolved issues that we listed before, like the correlation of the crop yield to, for example, parameters like fertilizers, irrigation, but also regarding the technology, we would like to know your impression, if you think it's something that could be really useful, and or you find it too complicated in your expertise, or you would like to explore more. Of course, there will be material that you can read, like tutorial, to try to explore yourself the platform and run the use case, not only the use case 3, but all the other use cases. If you are aware about alternative solutions that could be integrated in the platform and so on. So these were just a few bullets to start our discussion, and I thank you for your attention. And you have our email address in case you want to send us your comments instead of sharing them today with us. Thank you. I open now the floor for questions or comments. Of course, we don't know what is the background of the participants here. Someone maybe is more interested in the specific use of Earth observation data. Some others are more on the technology side. Depending, of course, on your expertise, you might want to deep more into specific aspects. Okay, it seems there's no questions or comments. Maybe everything was very clear, I don't know. Or maybe you just need to digest a little bit all this information. We are aware that it was quite a lot altogether. It was an intense workshop. And but the recording will be shared together with the presentation. So whenever you want to know more about both the technology and methodology, of course we can follow up on these. Maybe, Katja, I can ask you to share also the link to the YouTube channel. So that it's where it's the EO4EU channel that will contain the recordings from the different workshop, and we can you can of course look again into the registration or share it with other interested people. Thank you, Maximilian. Thank you. Okay, yes. So here you have also the link to the YouTube channel. And yeah, we will need just a few days to upload this recording as well. Okay. If there are no questions or comments, I guess we can stop here. And I thank you all for participating and all the partners for supporting in this presentation and the colleagues. Yes, I hope that we provide you with some insights today. Thank you all. Have a good day.
Thank you.
you.
Thank you. Bye.
Thank you. Bye-bye.
Thank you. Bye.
Thank you. Bye.
Bye. Bye.
Bye-bye.